Okay, hopefully everyone can hear me. Lineage first computing towards a frugal user space for Linux. Lineage and frugal are going to be the keywords here. And I'm going to talk about Shark, which is a platform we've been developing. But first, a detour, assuming I can operate slides. Oh, there we go. This here is a map of the increased probability of species extinction if you convert that land to arable, i.e. crop farming. So this is the result of, unfortunately, you can't see the names because it's been hidden by the Zoom thing. This is the result of like 2 to 3 years worth of work by about a dozen people and an awful lot of compute, which seems maybe a profligate use of resources just to tell you not to put a farm in the Amazon, but as a society, we keep doing it. And so apparently we need to do this. This here is a corresponding map, which is showing the decreased probability of extinction if you restore land to pre-human. Which is an interesting map because it's not always positive. Many species have flourished in arable landscapes like the UK, and therefore this map can help guide you as to where to do it. And that's interesting to say the EU has said by 2030 it wants to rewild 10% of land. Well, this map can help you work out where to do that to maximize the impact for biodiversity. These maps, as I say, are big kind of summaries of a lot of work and a lot of compute. And so we've been working with ecologists on this. This is primarily ecologists. I'm a computer scientist. And what happens over the course is like, this is exploratory research. Like when they start this, they don't know what they're doing. That's their job. It's a bunch of ecologists. Like you'll have one that'll ingest some data. They'll write some Python scripts to get some insight from that. They'll pass it to their colleague who maybe does some more processing, can't get it working. And then over the course of 3 years of individuals doing this, you end up at a pipeline like this. So this is the software pipeline to generate the maps that I showed you earlier. So there's kind of a lot going on here, but you only get this view at the very end. This is an established pipeline that you set up and run, that you get here eventually. This is, I was regenerating the maps last week. This is just a graph of how much energy it took. It took about a day and a half to generate those maps. It used 5 kilograms of CO2 equivalent just to generate two TIFFs, essentially. And that's when you've got a trained computer scientist who knows how to extract maximum performance. I'm pegging this machine. Like the ecologist, when I started on this, it took three weeks plus, and probably use closer to like 40 to 50. So that's an order of magnitude if you are just a vernacular software engineer whose expertise is in a different domain, right? This is the same graph. I just cut one of the variables. So you've got all the components here, but I've just kind of simplified the run. What you can see in this graph for this particular analysis, you've got some data ingestion at the top. There's a bunch of resizing of, reprojection of maps, kind of getting the data ready for your experiment. In the middle, there's a bunch of heavy compute to generate some standard biometric kind of analysis there. Then this is the kind of custom bit, which is another heavy compute stage. And then you've got a reduction towards the end to generate the maps for publication. And it's, okay, there's a bunch of boxes there, but it doesn't seem that complicated. Like, there's each one of these is a Python script and then a data file, and it just goes all the way down. The challenge for like the vernacular software engineer, i.e. not a computer scientist, but someone who writes software for a living, is like there's a lot of uncertainty in this, which leads to it being run repeatedly over and over again in full, or at least in significant portion. First of those uncertainties just comes from scale. Like for that map, they were processing 40,000 species off the IUCN Red List through 4 scenarios with 5 different extinction curves. So you just multiply all those together, and that's how many scripts they had to run for the individual species analysis. The maps are 150 gigabytes each because there are 100 meters per pixel at the equator, and there's 4 layers for each species calculation. These numbers just like even a beginning computer scientists would struggle with this. And so that just leads to, it's hard to understand what was done where and whether the data is out of date or whatever. So it's the easy resolution is just to rerun everything. There's other bits like this, like I highlighted, this is common work, but no one reuses that data set, even though it's a standard method, because no one quite knows what the other groups did. So lots of publications will be based on area of habitat maps, but that data, if it is shared at all, there's a bunch of variables that might have gone into it, and do we know what they were? So it just gets regenerated. And similarly for the end results, there is poor description of what went into the end results, and that's super important. Like particularly like when you're sitting at a Western university trying to tell the world how to live its life, you want to be able to make sure that your work is scrutable, challengeable, and reproducible. But that's not built in. And again, so if I want to reproduce some science, I just have to rerun it. I have to build the pipeline and execute it myself. Other sources of uncertainty, data sets change, update, like a 3-year project. The IUCN Red List of endangered species updates twice a year. Probably only a dozen species changed out of the 40,000, but it's just a big binary drop that gets shipped out through the API that we were using. And so again, easier just to rerun it all. These maps from the JRC are not versioned. They will update, but if you happen to run your pipeline in 1 month and then another month, there's a risk you'll get a different result. And we've lost some, we've actually lost time to this. And then finally, in the right, that's a diff between 2 maps generated using the same standard method in GDAL, the common geospatial library that the majority of people would be using. And so it's like if someone had not run apt update on one machine and had on another, you'd get a different result. All of this just leads to all this uncertainty. And again, the easiest thing, if you're not a kind of computer scientist, would just be to run it again. And so you've kind of got these 2 things here. Like, a lot of this just looks like dependency analysis. Like, if I could write a make file, wouldn't the world be great? This is how I live my life. So it's kind of like, can we work out how far back to what we've got is interesting? And then on the other side, we've got this kind of lineage, which is like, how much do I trust the data at any given point? Do I know what went into it? Do I know the specifics about each one? And so what we're trying to do on the computer science side is, how can we tackle this, and how can we tackle it for a vernacular software developer? Because what they're doing at the moment is not frugal. It's the opposite of frugal. I would say it's profligate. But that's not their fault. It's because we on the computer science side have not provided good tooling for this. This is kind of state of the art for an ecology pipeline. It's a shell script. This has none of the properties that we desire, but this is pretty good shell script. It doesn't have home directories coded into it, which, and things like that. But as a computer science, as I say, CI, is an established practice, so that's where we started. CI, obviously, I wouldn't want to wish upon an ecologist. I don't wish it upon myself, which is why when I was a manager of a software engineering team, I paid someone else to do it for me. Like, this is a whole job in itself. This is one of the other pipelines that we did over the last couple of years, being run through the current system, which is the CI system behind the OCaml package management service. So this is kind of well tried and tested CI system, and it has some good points and some bad points. Good points, it has a whole bunch of, like, it's container based, for instance. And that container image is part of the hash that says whether you need to rerun something. It's evaluated as part of the dependency graph. So that means if for GDAL versioning, for instance, would be picked up by this. Like, if there are library dependency changes, we'd know to rerun it or not to rerun it. And so there's a bunch of things around the containerization that's useful. It builds the graph, tracks things. The big downside is its interfaces are OCaml. And even I have a PhD of computer science from the University of Glasgow, and I haven't been brave enough to try editing this. So that's clearly a non-starter. So we've been working with a bunch of interfaces on how we can build this system for ecologists to be more accessible, to empower them to be more efficient and know exactly what is going on in these pipelines. So this here is the documentation for the map pipeline that I showed you earlier. It's a standard markdown file with the description and the stages to run. That is actually executable in our system. So we're building a system we call Shark, and it sits on top of the current CI system, but this is the input format for what we run. So these graphs I keep showing you, they're automatically extracted from that markdown file and form the AST through which Shark will then do its execution. It knows where all scripts are because it's in the same repository. We've got little annotations that don't show up there, which indicate which container image to use for which stage. And we've also done like wildcarding. So these kind of hard to see, but these blocks have kind of got a little 3D hint to them. So if you kind of put a directory name asterisk as an input to a stage, it can automatically infer parallelism. And that's actually a huge win because, you know, computers, like if I can run more processes across all the cores I have, it's much more energy efficient than doing it in a serial, even though like the time taken and energy costs are favor parallelism here. And so automatic extraction of that has been a big win as well. What I don't have a slide show is also like this is all Python, so we've been experimenting with shimming the Python to automatically detect what files it opens, what network connections it opens, and we stash that alongside each result. And so at the end, with the metadata for this file, I can extrapolate back the entire graph. We need to do better at that because not everyone uses Python, so we're looking into that. So there's much work to do here, but this is, I guess, trying to solve an exploratory science version of the kind of how do you make scientific pipelines efficient and usable for ecologists. That's my talk. Thank you very much.
Thank you very much.
There you go.
Okay, any questions? Jason has a question.
Oh, thank you. So yeah, very interesting talk. So at least for an end user ecologist that basically just is the one pressing the button causing the most emissions, is there stages when they're editing that to say, okay, I press this button and I have to recreate 6 executables, but there's 6 that I know that come from data I don't need to touch. Does this framework give the sort of the last one in the chain the option to like not run parts of that chain because they trust it?
Not as it currently stands. At the moment, it is more a traditional CI as we have it in that if I regenerate, if I ran this one recently, it won't rerun it again, and it'll only do things that have changed. There needs to be more control that we haven't got something more to do.
Thank you.
You just check if there's a question from online. Bakar, any questions?
No, we are still okay. Yeah,
Okay.
nothing here.
Go ahead.
Hi there, thanks very much. This is quite interesting because I'm looking at Python for an honours project in terms of making it more green. I was wondering, when you look at its framework, are you looking specifically at data analytic libraries and seeing how energy efficient they are in the process?
You don't need to repeat, so they cannot hear you. I forgot.
Okay, sorry. So yeah, so the question is like, what scale am I looking at? Is it just the high level orchestration, or are we looking at the libraries that Python itself is using? Both. So kind of one of the things I've not talked about, and I'll maybe chat to you later, is for the map loading and stuff, I had to implement. I've implemented a geospatial library on top of GDAL that does all the memory management, so you can load those 150 gigabyte maps as an ecologist and not think about the memory footprint, and it will juggle them. I think both are needed, to your point. Like some of the stuff's really good, like NumPy is fast, efficient, but some of the other ones are lacking still.